We are on FRQ topic number 9 out of 10. So we're almost to the end of our FRQ topic review. This topic is series convergence and divergence tests. Tomorrow or the next topic will be Maclaurin and Taylor series. Okay, for FRQs, these are the tests that you are asked to use. Okay, so I tried to make up a one-page review of the series convergence and divergence tests. It was kind of hard, as you can see by this sheet. It's hard to make it a one-pager of a review, but it's kind of jam-packed with information. Let's go through some of the important parts on here. First of all, what does it mean for a series to converge? A series converges when the sum, which is the meaning of a series, when the sum is one real number. That's what it means for a series to converge. The sum is one real number. If it's not, then the series diverges. Either it cannot be determined, maybe it's infinity, maybe it's negative infinity, maybe it oscillates between two or more numbers, whatever. Diverging means the sum is not one real number. Okay, and we have these tests, there were 8 of them, that determine whether a series converges or diverges. The first one is the nth term test. That is only for divergence. Only for divergence. See if it's top-heavy. If it is top-heavy, then the series diverges by nth term test. If the limit, as n goes to infinity, of your a sub n expression is not 0, then the series diverges by nth term test. That's the nth term test. If it is not top-heavy, then go to one of your other 7 tests. Geometric series test. If it's in this form, it's a geometric series. Alternating series test. Is it alternating in sign, decreasing in magnitude, going to 0? Then it converges. Alternating series test can only be used for convergence. Nth term test can only be used for divergence. Okay? I didn't mention this when I briefly discussed geometric series test. If the series converges, we can find the sum. We can find that one real number sum. Okay, using that formula. All right, so alternating in sign, decreasing in magnitude, going to 0, then the series converges by AST. If it does converge, if the non-alternating series also converges, then the alternating series converges absolutely. If the non-alternating series diverges, but the alternating converges, then it converges conditionally. P-series test. This form, and only this form. This is the only P-series form. 1 over n to the P. 1 over n to the P. It has to be a 1 to be a P-series. Okay? Converges if the P is bigger than 1. Diverges if it's less than or equal to 1. If P is equal to 1, then you have this, which is the harmonic series. And it does diverge. Comparison tests have a condition. Both series terms, the one that you're given and the one that you're comparing it to, must be greater than or equal to 0. All of the terms have to be greater than or equal to 0, which means you cannot use a comparison test on an alternating series. You cannot do it. Okay? So I use the comparison test if I have a polynomial over a polynomial. That's when I use a comparison test. Okay? Limit comparison is my go-to. Take the limit as n goes to infinity. Okay? If you get a finite positive number, then both series converge or diverge. Direct comparison is when you can see if your series is less than a known converging series, then your series converges. If your series is greater than a known diverging series, then your series diverges. Direct comparison test. Integral test has conditions. The function f of x must be positive, continuous, and decreasing on the interval that you need it to be. Okay, so if your function is positive, continuous, and decreasing, and if the function converges, the series converges. If the integral diverges, I think I said that wrong. If the integral converges, the series converges. If the integral diverges, the series diverges. Okay? They either both converge or both diverge. The ratio test we use when we have a complicated expression or factorials. Okay, it's another limit. Substitute n plus 1 in for n. Then divide by your normal a sub n expression. If the limit of the ratio is less than 1, then the series converges. If the limit of the ratio is greater than 1, then the series diverges. If the limit is equal to 1, then you use the ratio test on something that you should not have used the ratio test on. You cannot use it on polynomials and only polynomials. It will not work. You'll get a limit of 1. So use it when you have exponentials, factorials, things like that. Alrighty. This next page in your notes here is just another like a table. It has a lot of what I just talked about. Let's talk briefly about error bounds. Okay. What is the difference between alternating series error bounds and Lagrange error bounds? Okay, let's review an alternating series error bound. Here's the sum of the series. Okay? So it goes on and on forever because it's going to infinity, but the sum is this entire infinite sum. It can be approximated using a set number of terms, let's say 5 terms. We call that S sub 5, the sum of the first 5 terms. So this would be S sub 5, the sum of the first 5 terms. The error is the sum of all the remaining terms. That is the error. Okay? Now, if the terms are alternating in sign and decreasing in magnitude to 0, then the error bound is the absolute value of the very first term that you did not use. The whole thing is the error. The error bound is just that first term, the absolute value of the first term. Okay? All right, Lagrange error bounds. For Lagrange error bounds, S can be approximated by, S is approximated by a polynomial of a given degree. Let's say degree 6. The error is still the sum of everything that you did not use. The Lagrange error bound is, it's in Taylor series form. The maximum next derivative, x minus c to the next power, over the next factorial. All numbers. No x, no c, no f prime, all numbers. The terms do not need to be alternating in sign, decreasing in magnitude to 0 to use Lagrange. It's on all of them. Okay? Alternating series error bound. Only use it when your terms are alternating in sign, decreasing in magnitude to 0. You will be told how many terms to use in the approximation. Your error bound is the magnitude of the next term. Lagrange error bound. Use it when you are told to. You will be told what degree polynomial, not how many terms, what degree polynomial you're using. The error bound is always Taylor form of the next degree. That's error bounds. Alrighty, let's take a look at an FRQ on this topic, topic 9. We don't usually see a full FRQ that are only convergence tests. I've seen it done once, but usually they're combined with Taylor series, okay? But I have made up using the one that I have seen and combining a few that I have seen. I've made up some FRQs just for you to practice, okay? So there's none that I can just give you straight, okay? Because the one that I saw it on was on a secure exam. Okay. So I can't give it to you to take home. All right. So let's say that we're given that a sub n is this expression for n greater than or equal to 3. Let f be this function for x greater than or equal to 3. F is continuous, decreasing, and positive. Use the integral test to show that the series diverges. Okay, they're telling me what to do. I'm using the integral test. They have already stated the conditions, so I don't have to state the conditions. I'm going to go straight to the integral. The integral 1 over x ln x dx from 3 to infinity. Don't forget your boundaries. I will never forget the year I was teaching a student who practically refused to put boundaries every time he did the integral test, and it drove me crazy. Has to have boundaries. Okay, I'm going to do a little u sub. So I'm going to let u be ln x. Anytime you have an integral with a log, try to let u be that log. So u is ln x, du is 1 over x dx, which we have, 1 over x dx. Okay, so this becomes the integral of 1 over u du. What is my new upper boundary? If I let x go to infinity, ln of x is still going to infinity. So this is still infinity. If I let x be 3, this will be ln of 3. What is the integral of 1 over u? Ln absolute value of u. From ln 3 to infinity, but I don't want to put infinity up there. I'm going to make that a b, and out in front, I'm going to let b go to infinity. Squeeze that in there, or erase it and rewrite it, or cross it out and rewrite it. Okay? Put b in for u. Put b in for u, let b go to infinity. Ln of infinity is infinity. This is infinity. If I put ln of 3 in, it will not change it. Okay? Word of warning, do not write minus ln of 3. Don't write that. AP graders are not going to like it if you use infinity where you would normally see a number. This is just infinity. So, since the integral diverges the series diverges by integral test. So the very last thing you should do is make a statement. Okay? Do not just write diverges, because that would imply that the integral is diverging and you never answered the question. Okay? Part B. Consider now this infinite series. So we still have that same a sub n, but now it's alternating. Identify the properties of the series that guarantee that the series converges. And then explain why the sum of the series is less than 1/3. Okay, first of all, what properties make this series converge? What properties make this series converge? Okay. The terms, not the series, the terms are alternating in sign and decreasing in magnitude to 0. To 0. Therefore, the series converges. Okay, those are the properties of the series that make the series converge, guarantee that the series converges. Now, why is the sum of this series less than 1/3? Okay, why is the sum less than 1/3? Well, if your series is alternating in sign, this value right here is the largest it could be, right? Because we're starting with this and then subtracting a piece, not as big, and then adding a piece, not as big, and then subtracting a piece, not as big, etc., etc., etc. Your series is going to be less than, the sum will be less than that first term. So the sum is less than 1/3 ln of 3, which is less than 1/3. So I answered the second part of that question. Okay? Part C. Find the interval of convergence of the power series, this power series. Show the analysis that leads to your answer. The interval of convergence, ratio test. Okay, so I'm going to set up the ratio test. It has to have a limit of the ratio. I begin by putting in n plus 1 for every n I see. So I'm going to have x minus 2. If I put in n plus 1 for that n, I'm going to have n plus 2 there, over n plus 1 times ln of n plus 1. Okay, I'm dividing by the nth term, which is the same as multiplying by the reciprocal of the nth term. Okay, the absolute values are mandatory. Don't forget those. All right. Now, there is something that reduces here. There is something that reduces here. The x minus 2 on top and the x minus 2 on the bottom, they reduce, leaving a single x minus 2 on top. So this will be a single x minus 2 on top. N and n plus 1 do not reduce. Ln of n and ln of n plus 1 do not reduce. However, as n goes to infinity, As n goes to infinity, these plus 1s are irrelevant. Then the n's reduce, and the ln of n's reduce, leaving 1. Okay? So this limit is just this absolute value. To converge, we want the interval of convergence, so we set that limit less than 1, which means that x minus 2 is between -1 and 1, and that means that x is between 1 and 3, adding 2 to each piece. Okay? We want the interval of convergence. I got the interior of the interval of convergence. Now I need to check those boundaries. So when x is 1, I'm putting 1 in place of that x. I'm going to have the series -1 to the n plus 1 over n ln of n, which converges by AST. It is alternating in sign, decreasing in magnitude to 0. When x is 3, I have the sum, I'm putting 3 in for x. That's just going to be 1 to the n plus 1, which is just 1. Okay? That series diverges, as shown in Part A. We proved that using the integral test in Part A. So the interval of convergence is 1 is less than x is less than 3, but including the 1, not including the 3. Okay? Let's take a look at one more. See what else how else they could say these. Okay. Let f be this function. Find the slope of the line tangent to the graph of f at x equals 1. Slope of the line tangent. Well, that's f prime. So I need to find f prime. I'm going to use the quotient rule to find f prime. Quotient rule, I start up on top, take the derivative, and that's a 0. Multiply by the bottom left alone, but it's still just a 0. Minus is in the quotient rule. Now I'm leaving the top alone and multiplying by the derivative of the bottom, 6x minus 5. Divided by the bottom left alone, but squared. And now I just want to plug in 1 for x. Easy peasy. Okay. Part B. Using this identity, evaluate this integral or show that it diverges. Okay. This is f of x. They tell me to use this, so I'm going to. What they did there is they did the partial fraction decomposition for me, so I don't have to. Okay? Now I'm going to integrate each piece. This first piece is just a simple ln. 3 ln absolute value x minus 2. The absolute values are necessary. Put them in. Minus 9 times, okay, this is also an ln, but there's this 3 down there. The derivative is 3, so if we did a u sub, we would have a 1/3. If we did a U sub, we'd have a 1/3 there. So ln absolute value 3x plus 1. And we are evaluating that from 3 to infinity. Once again, I'm going to let b go to infinity here. Okay? So, if I just put b in now, I'm going to get infinity minus infinity, which is indeterminate. We don't know what that is. So you cannot put b in for x yet. All right? Instead, combine your logs. If you have an infinity up here, combine your logs. Okay? This 9 times a third is 3, so they both have a 3 out in front. So it'll be a 3 ln absolute value x minus 2 over 3x plus 1, like that. Okay? Don't forget your 3 outside. Now we can put b in for x and let b go to infinity. The minus 2 is irrelevant, the plus 1 is irrelevant, and we have b over 3b, which is 1/3 inside. So I have 3 ln of 1/3 minus, now I'm putting 3 in for x, 3 ln of 1 over 10. That's it. Done. Now, in part C, determine whether this series converges or diverges. State the conditions of the test used. You guys, we just showed that the integral converged. So I'm going to use the integral test because I already did the hard work for the integral test. Okay? But to do that, I need to say what I'm doing. F of x, which is this function, where I put x's in for n's, is positive, continuous, and decreasing. On the interval when x is greater than or equal to 3, x is greater than or equal to 3. That's the conditions. The integral 3 to infinity of f of x converges as shown in part B. Therefore, the series converges by integral test. Sorry, got out of your line of reading. Okay, converges by integral test. Okay, so that's a possibility of an FRQ that they could give. Okay? Alrighty, so that's a review of all of the series convergence. I did not review with you what would be necessary for a limit comparison test. Let me use this. Let's say that instead of already having found that integral converges, what if we hadn't done that? What if we just needed to use the limit comparison test on this? Let's do this using the limit comparison test. So here's my series. And let's just show that converges. I know it converges using the limit comparison test. So I'm going to compare with what series? What series am I comparing it to? 1 over n squared. This behaves like 1 over n squared, which is a converging p series. Both series terms are greater than or equal to 0 for n greater than or equal to 3. That's the condition for the limit comparison test. Now I need the limit. I take the expression they gave me, and I'm dividing by the expression that I'm comparing it to, but since it's a fraction, I'm going to multiply by its reciprocal. Okay, as n goes to infinity, these small guys here are insignificant. It's like they're not here. So I have 21n squared over 3n squared, which is 7. Finite and positive. You don't have to write finite and positive. 7 is finite and positive. I'm just saying that's what you're looking for. Therefore, the series that we were asked to determine convergence for does whatever this one did by limit comparison test. So that's the work that you would have had to shown had you done the limit comparison test rather than the integral test. Okay? All right.